Hi everybody. This is our lecture on section 2.3 on the dot product. Given two vectors f and d with angle theta between them, we have the following. So you have vector f, think of that as a force vector, and vector d, that's a vector of movement, where we're moving an object along that vector using force F. So we're explaining this in physics terms, and you've got some angle theta between them. So given this situation, right, if we take the tip of F and we draw this perpendicular from F down to D, tip of F down to D, and we have this line here. Let me zoom in. Then this length right here is the length of F times, well, this is opposite from the angle theta. So this is length of F times sine theta. And this length down here, the other side of that right triangle, is length of F times cosine theta. So we define the dot product as follows. Of F and D as follows. F, and then we put a dot, D, is equal to, well, it's the length of D times the length of F cosine theta. So it's this red length here times the length of D itself. Okay, that is the dot product. Notice the following. 1. If theta is 90 degrees, then F dot D is 0. 2. If 0 is less than or equal to theta is less than, strictly less than 90, then F dot D is positive, right? When theta is 90 degrees, cosine theta is 0, and it doesn't matter what these guys are, it's just 0. If theta is less than 90 degrees, if it's an acute angle, right, this length is positive, that length is positive, and cosine is positive. So the dot product is positive. If theta is strictly bigger than 90, and it's always less than or equal to 180 if you if you don't take the reflexive angle, then F dot D is negative, right? Because length of D is positive, length of F is positive, and cosine theta would be negative. So the dot product being positive, negative, or 0 depends solely on the angle between them. Okay? We say that therefore F and D are orthogonal, right? In other words, perpendicular. If and only F F dot D equals 0. Okay, so you can tell about the angle between F and D, whether it's acute, obtuse, or a right angle, solely on whether we are positive, negative, or zero with the dot product. Okay, so perpendicularity being, particularly noteworthy in that case. All right, so the physical meaning of F dot D in physics, if a force F parallel to the path, parallel to the line of movement of an object, a distance t. So we have a force F parallel to the line of movement of an object at distance d. So we're moving an object from 0 to d, and we have this force F that's acting on that object. Then the work done, this is how we define work, done on the object by F is just F times D, force times distance. All right, force times distance. And your units of measurement are newtons when force is in, when force is in newtons and distance is in meters, then your unit of work is newtons times meters. Right? Newtons times meters, also called joules, right? In English units, force is in pounds and distance is in feet or something like that. And the unit of work are foot-pounds. Feet times pounds. All right, so if F is not parallel to the if force vector F is not parallel to the vector of movement d for the object, then it is only the component of F in the direction of d that contributes to the work. The component of F in the direction of d that contributes to the work. The component of F that is perpendicular to d makes no contribution. Makes no contribution to the work. So we are back to this picture up here. Right, so you've got some force that's not quite in the same direction as the movement of the object. Right, so there's a part of F that's perpendicular to D, and then there's a part of F that's parallel to D. And the sum of those two parts is F itself, the parallel and the perpendicular part. Right, that's the third side of the triangle of this vector segment and that vector segment. Right, so F is just the sum of these two, right? F cosine theta, F sine theta, that is the vector F itself. Right, but it's only this part that's parallel to D that contributes to the work. So here, the work done by F by f on d is, right, the component of f in the direction of d times the distance moved. So it's force times distance. So in this case, it's equal to, right, the size of f times cosine theta times the distance moved, length of d, right, which is just equal to f dot d. So it's just the dot product, right? So when f and d are parallel, work is just force times distance. When f and d are not parallel, work is force dot distance. So it's still a product, it's just a different type of product, the dot product. Okay, so that's the meaning of the dot product in physics. All right, what's another way to calculate dot product? So if U is equal to A1, B1, C1, and V is equal to A2, B2, C2. So if we have vectors in component form, then U dot V, by definition, right, is U V cosine theta. Okay, but other than that, we will also get that U dot V is just the product A1, A2 plus B1, B2 plus C1, C2. So that's for three-dimensional vectors. So that's the first part of the theorem. Second part of the theorem is for two-dimensional vectors. If U is equal to A1, comma B1, and V is equal to A2, comma B2 for two-dimensional vectors, then same thing. U dot V is equal to A1, A2 plus B1 times B2. Pretty neat. So the proof of this fact, it is actually the law of cosines in disguise. And here you will see it. So we're going to do the proof just in two dimensions, just to simplify notations. In 2D only. 3D is similar. This takes more writing, so we'll just leave it out. It's the same idea. So if you've got two vectors, U and V, so here's U, here's V, and you've got some angle between them like that. What's this vector right here? All right, we covered that. All right, that is equal to U minus V, right? Because V plus U minus V should be equal to U, right? So that's tip to tail, head to tail. We've got V and U minus V head to tail. So this vector is their sum, and that sum is U. Okay, so given U, V, and U minus V like this, by the law of cosines, we get the following, right, that the length of U minus V squared is equal to the length of U squared plus the length of V squared. So I'm going to leave out the hats here just to simplify things. U minus V squared is equal to length U squared plus length V squared, right? That's Pythagorean theorem. When theta is equal to 90 degrees. If theta is not equal to 90 degrees, then it's minus this correction, 2U V cosine theta. But that's the dot product of U and V right there, right? So let's rewrite it as U minus V squared is equal to U squared plus V squared minus 2U dot V. right? That's the definition of the dot product right there. It's in the law of cosines. Okay, so now let's put these into component form. So u minus v is a1 minus a2, b1 minus b2. This is a1 or a1 b1 squared plus a2 b2, the length of that squared, minus 2u dot v. Alright, so, well, what's the length of a vector? It's the x component squared plus the y component squared, square root. Oops, but we're squaring the thing, so there's no square root there. So then this is a1 squared plus b1 squared, a2 squared plus b2 squared, right? I mean, it's supposed to have the square root for the length, but we're squaring it. So that goes away, minus 2u dot v. So let's multiply these out. a1 squared minus 2a1 a2 plus a2 squared. Move that over. Plus b1 squared minus 2b1 b2 plus b2 squared is equal to a1 squared plus b1 squared plus a2 squared plus b2 squared minus 2u dot v. So a1 squareds here cancel, a2 squared, b1 squared here and here cancel, and b2 squared cancels. So now I'm left with minus 2 a1 a2 plus b1 b2 is equal to minus 2 u dot v. Cancel the minus 2's, and we have that a1 a2 plus b1 b2 is equal to u dot v, right, which is our desired result. Done. One moment. Okay, so let's take an example. Let u equal 1, negative 1, 0, and v equal 2, 3, 2, right? Then u dot v is equal to, well, it's 1 times 2 plus minus 1 times 3 plus 0 times 2. So that's just 2 minus 3 is minus 1. Right, so you can calculate the dot product without the, referencing the length of u, length of v, and cosine theta. You just calculate it with these coordinates. Another example, let u equal 1, 1, 1, and v equal to, 1, 2, minus 3, then u dot v is equal to, well, it's 1 times 1 plus 1 times 2 plus 1 times minus 3, which is 0, right? So u and v are perpendicular. Right, so you can tell when u and v are orthogonal just by, checking a product and sum of components. All right, it's pretty strong result. Even a little bit deeper than this is the following. Consequence. All right, so u dot v is equal to length u, length v cosine theta. So u dot v over length u length v is equal to cosine theta. So the inverse cosine function of u dot v over length u length v is the angle between the two vectors. So for example, right, we'll say u is equal to, so let's just make up a vector, 1, 2, and then v is equal to minus 3, 5, and then we've got this angle theta in between. Let's find theta. Okay, well, cosine theta is equal to u dot v over length u length v. So it's equal to minus 3, 1 times minus 3, 2 times 5, plus 10, over length u, which is square root 1 plus 4, length v, which is square root 9 plus 25. Alright, so this is equal to 7 over, so this is root 5, root 34, so 170. It's 7 over root 170. Alright, so theta is equal to arc cosine 7 over root 170, which is approximately equal to, pull out our calculator. So a couple different places where you have calculators readily available on your computer. There's the Wolfram Alpha as well, but you can also just plug it into here on pull up your Google Chrome or other browsers, and it should just calculate the number for you. It's just built in, or it uses the web or something. I'm not sure. So 7 divided by 170 to the 0.5. Boom. So this is in radians. I would rather have degrees. 57.5288 degrees. Okay. So, the cosine of theta is just calculated using coordinates of vectors. Dot product divided by lengths. Right. So there's no funny calculations going on in there. It's all just standard arithmetic to calculate cosine theta. To calculate theta, then you have to do some more fancy calculations with the arc cosine, but anyway, that's what you have. Here's another problem, another example. Let u equal 1, 2, minus 3, and v equal 2, 1, t. Find the value of t. U and v are orthogonal. Alright, find the value of t that would make these two vectors orthogonal. So actually there always will be one. Given a vector u and a vector v with one unknown component like that, you're always going to have one that's orthogonal, because one value of t that makes it orthogonal, because the dot product being 0 just governs when these guys are orthogonal. So the dot product is going to be 2 plus 2 minus 3t. And there's always a solution for t in such an equation. Right, so we have 0 is equal to 4 minus 3t. So 4/3 is t. Right? So So these vectors are orthogonal. Let's check it. All right, we've got 1, 2, minus 3 dot 2, 1, 4 thirds. All right, so this is 2 plus 2 minus 4, which is 0. All right, so that checks out. All right, final topic in this section. Projections. Let's go back to that picture of those two vectors from before, f and d. All right, we'll call them just u and v in this instance, since we're not necessarily talking about physics, just talking about the vectors in general. Here's u and here's v. Right, this one here is the length of u sine theta, and this one here is the length of u cosine theta. That's just the lengths, the components. But what if I want to find the vector itself? So this vector itself and that vector itself. So this vector is called the projection into the direction of v of u. The projection of u onto v. Onto v. This vector here is called the, well, we write it as orth vu, and that's the component of u, or that is orthogonal to v. So that's the component of u in the direction of v, the projection of u onto v, or the component of u in the direction of v, the component of u in the direction of v, and that's the component of u perpendicular to v. And notice that u is equal to the sum of these two vectors. It's equal to the projection onto v of u plus the orthogonal component of u to v. All right, it's just the sum of those two. So basically we're just going to find the projection. We're going to find the projection and then subtract it from u to get the orthogonal bit. Right? So here it goes. One more page. Okay. Well, we have already seen that the length of the projection onto v of u is equal to length u cosine theta. So that's what the length of that projection is supposed to be, just from some trigonometry. And a unit vector in the direction of v is 1 over the length of v times v. All right, so 1 over the length of v times v is a unit vector in that direction, the direction of v. So the projection is this directional vector times that length, just the product of the two. So the projection to the direction of v of u is equal to length u cosine theta over v times the vector v itself. Right? But we can rewrite this as length u, length v, over length v, forgot the cosine theta. Length u, length v, cosine theta, over length v times v. Right? I just uncanceled length v, one factor of length v like that. And the reason why I did that is because, well, now this is just the dot product. Right? That's u dot v. And length of v times the length of v is actually v dot v times v itself. So that is a nice little formula for the projection of u into the direction of v. So we use the fact u dot u is equal to the length of u squared. Right? So we use that fact there. Here we have the length of v. Well, I guess I'll do it with the v. The length of v squared is equal to v dot v. So length can be written in terms of dot products as well. The length of v squared is equal to v dot v, and we use that right there from here to here. This is length of v squared, this is v dot v. So now, the orthogonal component to the orthogonal part of u, the part of u that is orthogonal to v is therefore just equal to u minus this thing here. U dot v over v dot v times v. Alright, so we've got the projection of u onto v and the component of u orthogonal to v. So for example, so let's take u equal to 1, 2, 2, and v, excuse me, equal to 3, 3, 0. Right, so now the projection of u in the direction of v is u dot v over v dot v, or the length of v squared. Let me rewrite it like this. Just the length of v squared. So you can use either or. Times v itself. So u dot v is 3 plus 6 plus 0 over v dot v is 9 plus 9 plus 0 times v itself, 3, 3, 0. So this is 9 over 18, right, which is 1/2. So this is equal to 3/2, 3/2, 0. Okay? So that's the projection of u onto v. That's right here. Do it in red. All right, this is the orthogonal bit. And this is the projection. So now let's find the orthogonal part. So the part of u that's orthogonal to v is just equal to u minus this one here. 3/2, 3/2, 0. So that's equal to 1, 2, 2 minus 3/2, 3/2, 0. So this is equal to 1 minus 3/2 is minus 1/2. 2 minus 3/2 is positive 1/2. And 2 minus 0 is 2. Notice these two vectors are orthogonal. Let's check to see that the projection of u onto v dot the orthogonal component of u to v is equal to 0. Let's see that they're actually perpendicular. Well, this is 3/2, 3/2, 0 dot minus 1/2, positive 1/2, 2. So the dot product is 3/2 minus 1/2, so that's minus 3/4. 3/2 times 1/2 is positive 3/4. And then 0 times 2 is just 0. So that whole thing is 0. So that checks out. So those two vectors are indeed orthogonal, and their sum is equal to v itself, right? That's v, or u itself. That's u right there, and u minus the projection is the orthogonal bit. So the sum of the two is obviously back to v. Back to u. Excuse me. All right. One other thing that we should mention, just some basic algebraic properties of the dot product. One u dot v is equal to, it's commutative, v dot u. Basically because addition or because multiplication of real numbers is commutative. 2, u dot u is just the length of u squared. 3, u dot the 0 vector, of course, is going to be 0, the scalar. 4, u dot kv. So if you take the scalar multiple of v and k and the dot product with u, that's the same as k times u dot v, which is just k times u dot v. Alright, so when you take the scalar product of u or v, and then you take the dot product with the other, then you just get the dot product multiplied by that scalar. Okay, so just some there's another one. U dot, this one's interesting, v plus w. All right, you do have distribution. It's u dot v plus u dot w. So dot product, just like ordinary product, distributes over vector addition, just like ordinary products distribute over ordinary addition. Okay, so some nice algebraic properties of the dot product, and this one is important as well. Okay, all right, so that is the end of the lecture on this section.